let me tell you a story. It's about a crisis that's brewing right under our noses on a scale that's almost impossible to wrap your head around. It's about the future of the internet, the absolute limits of our technology, and, believe it or not, a tiny solution that's been hiding in plain sight for over 1,600 years. Just look at this number, 475 exabytes. Now, this isn't some wild guess about the future. This is how much data traffic is hitting the global internet every single month, right now. So, what in the world does a number this huge even mean? And what is it telling us about where we're headed? Okay, to get our heads around this, let's try to put it in perspective. You know what a gigabyte is. Well, 1,000 of those is a terabyte, 1,000 terabytes is a petabyte, and you need 1,000 petabytes to get to just 1 exabyte. We are talking about an absolutely astronomical amount of information every single month. And here's the kicker, 475 exabytes is just where we are now. As you can see from this chart, we're not just on an upward curve, we're on a rocket ship. By 2030, that number is set to just explode. We've got billions more people and devices all coming online, which means a true tsunami of data is heading straight for us. And this data tsunami, it comes at a huge, huge cost. See, every single byte, every photo, every video, every email has to be stored and processed in these massive data centers all over the world. And they are already struggling to keep up. Their energy use is growing by 10% every year. Think about it. A single Google search emits a noticeable amount of CO2. Now multiply that by trillions. So you might be thinking, okay, just build more data centers, right? Well, it's not that simple. The problem is we are slamming headfirst into a fundamental technological wall. The very tools we use to build this amazing digital world, well, they're reaching their physical limits. And this slide just lays out the problem perfectly. On one side, you've got electronics. We're brilliant at making them tiny, down to the nanometer scale, but they're slow. They're stuck in the gigahertz speed limit because of something called RC delay. It's basically the traffic jam that happens when you're trying to charge and discharge tiny circuits billions of times a second. Then, on the other side, you've got photonics, using light. And light is crazy fast. We're talking terahertz speeds. But it's big. Light just refuses to be squeezed into a space smaller than its own wavelength. So we're stuck in this trap. We can have tiny and slow, or we can have fast and big. To solve our data problem, we desperately need both. This feels like an impossible problem, doesn't it? It sounds like we need to somehow break the known rules of physics. But what if the key to all this wasn't dreamed up in some futuristic lab, but was actually found in a museum? You're not going to believe this, but it turns out the Romans, completely by accident, stumbled upon the core principle that could get us out of this mess. Check this thing out. This is the Lycurgus cup. It's a Roman chalice from the 4th century. And for hundreds of years, it completely baffled scientists. Here's why. When you shine light on it, it looks kind of like this murky green. But when you shine a light through it from the inside, it glows this brilliant, almost magical red. So how on earth is that possible? Well, the secret is, and I'm not kidding, ancient nanotechnology. The Roman artisans who made this cup had, without knowing what they were doing, mixed microscopic particles of gold and silver right into the glass. We're talking particles so small, nanometer scale, that they are literally tinier than a single wavelength of light. And at that tiny scale, they start messing with light in really weird ways, which is what creates that incredible color-changing effect. So that ancient cup, it wasn't just some cool artifact. It was a clue, a massive clue. It showed us that if you create the right conditions, you can grab hold of light and control it at the nanoscale. And this accidental discovery has given birth to an entire field of science dedicated to, well, putting light on a leash. And that field is called plasmonics. Okay, that definition sounds like a total mouthful, I know. But here's the simple version. It's the science of using tiny metal structures, just like the gold and silver in that Roman cup, to grab light and squeeze it into spaces that should be physically impossible, totally shattering that diffraction limit we talked about. So how does this magic trick actually work? Well, the source material gives this fantastic analogy. It says to think of all the free electrons inside a piece of metal like a single piece of jelly. When light comes in and hits it, this whole electron jelly starts to wobble and ripple in a collective wave. That wave, that ripple of wobbling electrons, that's called a plasmon. And this is the absolute game changer. By turning light into these tiny plasmon waves and then back into light again, we get the best of both worlds. We get the ridiculously small nanometer size of our best electronics, combined with the mind-blowing terahertz speed of photonics. That two-cornered problem we had, Plasmonics solves it. It's the breakthrough we've been looking for.
All right, so this is way more than just a cool physics trick. This breakthrough unlocks a future that honestly sounds like it's straight out of science fiction. So let's take a look at what this actually means for all of us.
Using plasmonics, we're talking about developing nanoparticles that can hunt down individual cancer cells, and then we can use light to make them heat up and destroy only the tumor. We could create solar cells that are hyper-efficient, absorbing way more of the sun's energy. We could build sensors so sensitive they can detect a single molecule of a virus. And to bring it all back to our data problem, we can finally create computer chips that communicate using light, just smashing all our current speed limits, and even create something called 5D optical storage that could hold terabytes of data on a tiny little disk that lasts for thousands of years. So here's the big takeaway. If you think about it, human history has always been defined by the materials we learned to master, right? The Stone Age, the Bronze Age, the Silicon Age. All the work being done in plasmonics today suggests we are right on the verge of the next great leap forward. And it leaves us with this incredible question to think about. What kind of world will we build when we finally learn to master light itself?